Hello everyone, so my topic today is about the dynamics of a viscoelastic turbulent flows at the limit of high Weissenberg number, high effects of polymer elasticity. We have some interesting findings that we think have very important implications on how we understand drag reduction in turbulent flow, especially the maximum drag reduction behavior by polymer additives. My name is Li Xi, I'm from McMaster University, and the work presented here is done by my former PhD student Lu Zhu here. So a lot of us are familiar with the polymer drag reduction phenomena. We know that adding polymers into a turbulent flow can drastically reduce its friction drag with even a very low amount of polymer addition. Intuitively, we can think that if we have a given pipe or channel, if we fix a pressure gradient between the two ends of the flow geometry, uh, we can get a higher flow rate for polymer solution compared with that Newtonian turbulence. That means without polymers. Obviously, there's a lot of interest here for its fundamental mechanism, but also for its practical applications, which can potentially reduce energy consumption in turbulent flows. So well, unlike Newtonian flow, which is only captured by one parameter Reynolds number, once we introduce polymers, we introduce a few more parameters, so we have a high dimensional parameter space. So one of the most important one is Weissenberg number, which measures the effects, the strength of a polymer elasticity on the fluid. So as for a given Reynolds number, as you increase Weissenberg number, you can have several different regimes of behaviors. Without going into much details, we know that as you increase the Weissenberg number, the flow rate will go up, right? That's what's plotting here is basically mean velocity profile. So flow rate will go up for increasing Weissenberg number. That's essentially the drag reduction effect. So initially we have what we call the low drag reduction regime, then high drag reduction regime. Today we are going to focus on the maximum drag reduction regime. Basically, once your polymer elasticity is strong enough, your drag reduction effect will hit an upper limit, and once you hit there, you cannot go further. So obviously, there's a question of why do we even have this limit? So why can't we keep on increasing the mean flow? Why can't we keep on reducing the friction drag as we introduce polymers until it becomes fully laminar flow, right? So there must be something else that keeps the turbulence sustained even at the MDR limit. That's what we call the existence question of MDR. The second question is equally interesting, that basically the MDR limiter is insensitive to polymer properties. That means that if you change the polymer solution, you change the concentration, or you use a different type of polymer. So even though that the rate at which you converge to the MDR will be different depending on what polymer solution you are using, but eventually all different polymer solutions, if they hit the maximum drag reduction, they hit the exact same limit. So why does this MDR limiter seem to be universal with respect to different polymer properties? And finally, we know that the MDR is captured by an empirical work formula, the work asymptotic. So any answer we find must be able to also explain why does it hit this particular level. So because MDR has been a limit at which your mean flow is not changing with increasing Weissenberg number, with increasing polymer concentration, therefore it is very intuitive for us to think about the MDR being some sort of a ultimate flow state. So the flow state can no longer be changed by polymers. And this has been a guiding assumption for nearly all MDR research for over decades. And in today's talk, we are going to examine whether this assumption is still the best one that we can make. So there has been many theories regarding MDR, but they explain MDR differently, but they all rely on the same assumption that MDR is some sort of ultimate flow state. They only differ in terms of what is this specific ultimate flow state. So there are two very promising ones in the past decade. One was proposed about 10 years ago. So it basically says that in turbulent flow you have roughly two kinds of turbulence. One is very strong, you call it active turbulence. The other is really weak, you call it hibernating turbulence. So you have both types even in Newtonian flow, that means that without polymers. But in Newtonian flow, this one basically takes most of the time, and this one is very rare. Once you have polymers, polymer only interacts strongly with a strong turbulence. So polymer will have very strong suppressing effect on active turbulence. But once you hit hibernation, polymer effect is really small. So what that means that as you increase Weissenberg number, this one keep on being suppressed, while this one is not changing. Therefore, the overall frequency of this one and the statistical importance of hibernating turbulence becomes higher and higher. And because there's a lot of similarities between hibernating turbulence and what we know about MDR, so it was hypothesized that the MDR is a limit in which active turbulence becomes rare and hibernating turbulence becomes the overwhelming majority. This picture can really well explain both the existence and universality of MDR, because this hibernating turbulence is essentially a structure that is fundamentally Newtonian and not affected by polymers. The problem is that we don't have enough evidence for this picture. So far, direct numerical simulation cannot capture this limit in which hibernating turbulence is overwhelming majority as has been hypothesized. The second picture relies on the finding of a new kind of flow instability that's called elastoinertial turbulence. That's basically a new turbulence-like flow instability in which both the inertia and the elasticity by polymer are driving the instability. So this kind of instability is very easy to be distinguished from that of a traditional classical, what we call inertia-driven instability or inertia-driven turbulence. So in the classical inertia-driven turbulence, we know that the vortex will align in the direction of the flow, whereas in EIT, the vortex will go sideways, right? So it's a very different structure. And because EIT occurs at the limit of high Weissenberg number, high polymer elasticity, and that's also a limit where MDR occurs. So it is very intuitive for researcher to assume that that's MDR is essentially the limit of EIT. More recently, it was found that EIT can be a self-sustaining instability even in a strictly 2D geometry, and therefore it has been further led to hypothesis that any kind of three-dimensional structure you see in a high Weissenberg number flow is just some sort of residual behaviors coming from classical inertia-driven turbulence. And at the limit of MDR, you would expect that these kind of structure will go away as Weissenberg number increases. So EIT goes to the purely 2D form. Also, MDR is a purely 2D form of EIT. The problem with this explanation is that for any flow instability that's driven by elasticity, we would expect that it will very strongly dependent on, it will be very sensitive to polymer properties. So how do you reconcile this fact with the observation that the MDR is similar universal with different polymer properties? So basically, both the existing scenarios are facing challenges here. So before we show our results, just a very quick walkthrough of our simulation protocol. We look at channel flow, in which the fluid is sandwiched between two large plates, and the flow is driven by a constant pressure gradient. And we can use Navier-Stokes equation to solve for the velocity and pressure field. We use a Fini-P constitutive equation to capture the polymer conformation polymer stress. And once we couple these equations, the coupled system has 4 parameters, and we'll basically explain the parameters as we see the results. So first of all, we capture the 2D EIT using our code as a few previous groups has done before, and we capture the characteristic structure of EIT, including the Y structures here are basically span-wise rows and span-wise vortices we have talked about before. Then the colors here show the level of polymer extension, so they basically shows a very distinct type of sheet like structure in polymer extension, which is also known for EIT. And we start by checking this hypothesis that the EIT is a pure form of a 2D EIT. Sorry, MDR is the pure form of 2D EIT. So this can be easily done. We just check the EIT solution for different Weissenberg number and for different other polymer properties. So what's surprising here is that as we increase Weissenberg number, we can see that the friction factor, the friction drag does not go down, but it goes up. More importantly, it keeps on going up with there's no sign of convergence at all. We also look at a different B parameter level. So the B parameter basically measures how much you can stretch a polymer chain compared with its equivalent structure. So we can see that for different B level, the pure 2D EIT solution, the friction also keeps on going up as the Weiss number increases. Also for these two different B levels, the two curves, they are not the same. So apparently what we're seeing here that at a high Weiss number, 2D EIT does not show the universal friction drag as we expect for MDR. However, if we have a 3D flow, we can show very clearly that as we increase Weiss number, the friction drag is going down. So we have drag reduction rather than drag enhancement. And at high enough Weiss number, it converges to a plateau. Right, and we can see that this is also 3D solution, mean velocity profile also collapse together at a high enough Weissenberg number. So that's the take-home message. We can only have converged mean flow in 3D flow. So the 2D EIT, it at least is not a simple answer. To further look at the dynamics of this 3D flow, we project the dynamical trajectory. So show here the dynamical trajectory in 3D turbulence is showing in this color varying solid line here. So we project this trajectory with respect to a few flow states that we know. So this region is active turbulence. So if we had a Newtonian flow, you would expect that your flow will spend most time here. So what happens here that if you look at this Weiss number equals 40 trajectory, so it spends sometimes in this active turbulence, but it runs away in two kinds of cycles. One is these smaller cycles. So it will go to this so-called edge state, which is basically governs the laminar turbulent transition, and it will come back. We call this type A cycle, and this is essentially the same as the previous active hibernating bursting cycle that we knew 10 years ago. This was the first scenario I discussed before. However, at this 40 Weissenberg's 40, we also observe a new kind of cycle. So in some of the instances in which once your flow escapes active turbulence, it doesn't really go directly to edge state. It will bypass edge state and it go to the region of further lower drag, weaker turbulence, but eventually will bounce back as it approaches EIT. Right, so you will approach EIT first, spend a lot of time there, then bounce back, go back to the hibernation turbulence, then go back to active turbulence. We call this a new type of cycle, type B cycle. And if we further increase Weiss number, we look at really high Weiss number. We see an entire different kind of behavior. We call this a type C cycle. So in this case, it seems to bounce back and forth between hibernating turbulence and the EIT. And compared with type B cycle, it samples a much smaller region in the state space and doesn't really go back to active turbulence anymore. So this is just time series of these new dynamics. The green line here is just an instantaneous magnitude of your friction factor, whereas the red line here is basically we measure how much energy has been exchanged between turbulent kinetic energy and the polymer elastic energy. So for Weissenberg equals 40, we see this very interesting intermittent behaviors. So these spikes correspond to instance of active turbulence, right? Let's return to the form of turbulence that's closest to Newtonian turbulence. Then you have two kinds of dips. These kind of shallow dips, they typically last a few hundred time units. These correspond to hibernating turbulence. So this is basically the old active hibernating cycle, which we call type A cycles. And we also have this much longer, deeper dips during which we can see that the elastic conversion energy, elastic conversion rate becomes positive. That means that instead of suppressing turbulence, your polymer is actually fueling turbulence. And this is basically represents the visits to the region that's near close to EIT. This is what we call the type B cycle. As you keep on increasing Weiss number, type A cycle start to disappear. Type B cycle become longer and longer. Then at a really high Weiss number, you can see that both type A and type B cycles has been gone, and you see this new type C cycle, which is reflected as some sort of wiggle in this time series, and you can see that the elastic conversion rate basically fluctuating back and forth in a quasi-periodic manner. So this is just summary of what we have seen here. So as we increase Wise number from Newtonian limit to a very high Wise number, so roughly up to about 40, we see type A behavior, which is what we knew back to 10 years ago, active hibernating turbulence transition. Then you have this transition to type B cycle up to about Wise number equals 64. Then after that, you have a type B cycle start to dominate. Then up to about 200, you see that type B cycle has go away, and you have this quasi-periodic type C cycle that become dominant. So remember that in 3D flow, when your Wison number is high enough, the friction drag will converge to a steady level, right? Which regime that is? That is basically the whole regime for Wise number higher than 64. So we can see that behind this converged drag reduction, behind this is seemingly the same level of mean flow, the same level of friction drag. There are at least two different types of dynamics, type B and type C. So behind this universal MDR limit, there's not one single type of dynamics. There's at least two types. But that's not even the end of story. We further can look at the time correlation function of the instantaneous fluctuation in the friction drag. So for Wise number equals 100, which is still within type B cycle, you see kind of a monotonic decay, which is representative of this intermittent chaotic behavior. But starting from Wise number equals 200, we start to see these kind of oscillations here, which represents this quasi-periodic dynamics in type C cycle. What's interesting here is that as you increase Wise number from 200 to 400 to 800, the fluctuation keeps on increasing, and the period becomes longer and longer. So even the type C dynamics keeps on changing as you increase your Wise number. So behind the seemingly converged level of drag reduction in MDR, the underlying dynamics keep on changing. So it is not one unique flow state that's mapping to MDR. It is a series of different dynamics which is keep on changing with increasing Wise number. So we don't fully understand type C cycle as yet. So we know that it's some sort of a quasi-periodic oscillation. What's plotting here is basically the blue line is the production of turbulence by inertial effect, whereas the red line is again the conversion of with elastic energy. So we see that even though the elastic energy is important, but still the production is essential. Actually, production goes through high and low cycles, and at peak of a production, if you remove the polymer effect, you can see that the turbulence will go all the way to Newtonian turbulence. That means that at this moment, the polymer still acts as not a driving force for instability, but it's suppressing instability. Whereas at the bottom of the production, if you remove the polymer effect, if you remove the polymer stress, then the flow will laminarize. So that means that at this phase, the polymer is important to the sustenance of turbulence. Finally, some direct flow images. So for type B cycle, it's between active turbulence, which we have this streamwise vortices, and EIT kind of structure, which we have this spanwise vortices. For type C cycle, you see two kinds of structures as well. This one seemed more like the EIT we knew, but this one have very distinct hairpin-like structures. Again, this exact dynamics of EIT is still something a topic of a continuous study. So to conclude, we show that with the increasing Wise number, there's three kinds of dynamic cycles from type A to type B to type C. Both type A and type C contains at least EIT as part of its cycle. Therefore, if you remove EIT, the turbulence cannot be sustained. But the most important message here is that for the entire MDR regime in which the mean flow has converged, the underlying dynamics keeps on changing. Therefore, there's no single ultimate state that's responsible for this converged mean flow at the MDR, and that challenged us. That's basically challenged us to rethink what we have been assuming about MDR. Also, that previously in the literature we use the term EIT to refer to as if it was one type of flow instability. Now we have shown that the kind of EIT we see in 2D and in 3D are different. So what do we what do we define the term of EIT? Do we still refer that to a single flow state, or do we treat that as a general umbrella term for a much wider range of instability? That's also a question that we need to discuss. With that, I thank you for your attention. and I hope you enjoyed this presentation.